I'm Dr. Balasubramanian Chandrasekaran, Assistant Professor of Computer Engineering from the University of the Pacific, and the topic I will be presenting today is Human-Robot Interaction in Multi-Robot System Framework for Industrial and Other Applications. The agenda for the presentation is abstract, introduction, literature review, integration into the existing robotic framework, conclusion, and references. In this paper, a review of some of the human-robot interaction techniques used in multi-robot systems is presented. The knowledge gained from this review will help in the understanding and development of an interface for human-robot interaction for the multi-robot framework for field or environmental monitoring. This is a research in progress. Human-robot interaction is an important and critical component while developing multi-robot systems to provide more safety and reliability of the system. In this paper, a review of few of the HRI methods and techniques in literature is presented, and each of the sections discusses about the HRI in a multi-robot system, followed by conclusion and references. The first one is the Robot System Assistant, ROSA. In this paper, the authors describe ROSA, which is a robot system assistant using facial, gestures, and voice-based recognition in human and robot interaction. It uses robot operating system and is modular and extendable. It also uses the concept of contactless, allowing for multi-device and multi-user implementation. The authors mention about the Wizard of Oz study on different communication modules for human-robot interaction. It also proposes a WOZ framework, ROSA, which is a robot system assistant. The system was actively controlled by a Wizard module, and a stationary cobot was used that can interact with the users through speech, gestures, etc. The Wizard module handled the monitors of users and the robot operation using the rules, and the figure shows the setup of the robot. The robot used is based on UR6E industrial robot having an RG6 gripper. The experiment was for cube stacking, and the robot has to pick the black and white letter cubes placed on the table. To highlight the objects, there is a use of camera and projectors above the table, and this can be referred to as workstation. Touchscreen and camera with a microphone was on workstation 2. In the third workstation, there was a robot having TOF and color camera. And figure 2 shows the schematic. The second method is the human decisions behavior model. In this paper, the authors describe a multi-robot interaction system that uses a station for processing data and cognitive system used based on decision-making process. It uses null space-based controls and traditional drift diffusion models in the system. The studies of multi-robot systems indicate the various applications. The authors mention that in a situation with multiple robots, the task conflicts can hinder a robot from completing a task and methods beyond the traditional behavior control. The use of null space-based behavioral control, also known as NSBC with task priorities, is used. The priorities can be reconfigured in a changing environment to handle uncertainties. The presence of human role as a supervisor for global behavior selection, intervene if necessary, and role as an active to provide control inputs or trajectory details for the robot is necessary, and therefore human-robot interaction or intervention becomes irreplaceable. However, the use of correct model is required for both the supervisors and the active roles in the HRI system. The social context DDM is efficient, and DDM uses actual information from sensory inputs instead of probabilities or human trust while making decisions. Figure 4 shows the human decision-making model schematic diagram. So this is the schematic diagram for making the decision under human intervention. In the third literature review, the multi-robot interaction interface with PICT, the authors describe an IoT-based multi-robot interaction interface using the open source platforms like Qt and PyQt5. Now, there are capabilities such as motion control functions for video monitoring, and other functions like a display interface can be created using the Qt and the PyQt5 for writing programs. Now, 5 sub-interfaces form the interactive interface system, and perception layers has sensors on the robots to acquire the environmental information. The information is then used by the WLAN in the network layer and sends it to the application layer. Ubuntu 16.04 was used, and Python was also used in the development platform. The navigation framework includes both the navigation and the positioning, which helps the robots to arrive at the targets from the initial state, and also determination of the robot's body position with respect to the environment under consideration. Move base package and AMCL package help in the implementation of the navigation. Gazebo simulation space helps with the capabilities to test the interface system. Overall, this system built using PyQt interface can operate easily and is stable when additional functionalities are added. So this is the interface system structure and the navigation framework structure. In the fourth paper, that literature review, ROCO multi-robot collaboration method is presented, where it deals with high-level communication and low-level path planning through the use of large language models known as LLMs. The collaboration method for multi-robot involves components such as task coordination and in a style of dialogues. LLMs use feedback to generate better subtasks, plan and motion planning in joint spaces. In the initial setup, a dialogue is set up between the LLM generated agent and the particular robot. The robot receives the information that is specific to it, and it responds according to it, such as I am Alice, I can be reached. As soon as the round of dialogue finishes, the subtasks plan is summarized by the last speaking agent, and each of the agent gets the subtask and possibly the 3D waypoints. So the validations such as parsing of text, constraints of tasks such as the inverse kinematics, checks for collision and optionally valid waypoints is also done while planning for paths. As soon as the validations are passed, the plans for the subtask combined with the inverse kinematics is jointly executed over all the arms. However, each of the individual steps of the waypoints for the task base can provide an intermediate configuration for the goals. The RRT-based motion planner in the multi-arm configuration uses the goal configurations to plan all the robot arm plans. Overall, it basically is another approach for collaboration between multi-robots, which uses large language models to aid with coordination and planning for the robots in the given workspace. So this shows the ROCO benchmark for multi-robot collaboration and the several components for the ROCO collaboration method. This shows the block sorting between the robot and the user in the ROCO multi-robot collaboration method. Now, in the integrating into the existing robotic framework basically is done through some of the literature review that was covered, and the goal is to include 3 robots in a navigating field and monitoring the field for crops for health and also objects in the field. Information collected by the robot will be through LiDAR, and the LiDAR can also be used with other sensors on the robot. The data will be used by the farm workers who can keep track of the agricultural field. There's a camera to do object detection, and when combined with the LiDAR data, it can give a complete picture of the environment. The framework is actually a work in progress, and the next step will involve simulation using the robot operating system. And a physical robot like TurtleBot will be used. So this is the overview of the framework within each robot. We can see there's an obstacle detection and avoidance, and the Raspberry Pi camera along with the LiDAR is used, and therefore there can be an obstacle detected, and the robot will take an alternate path, or the robot basically is in a situation where it needs to contact the user, and the user can actually guide it out of uncertainty, and the robot resumes the autonomous mode. In conclusion, this paper, a review of few papers on multi-robot collaboration and HRI, is presented. The review will be used towards the design and development of a human-robot interface, which will be integrated to the framework for agricultural field monitoring. And as the research progresses, there will be an update to the framework, and a fully functional robot will be developed, which is the next step of this research. These are the references used in the paper. Thank you.